Tonight, we're going to explore something that sounds like science fiction, but is actually one of the most intriguing mysteries in modern astronomy: a planet. You've probably heard whispers of it in headlines or passing conversations. Scientists talk about it when discussing strange movements far beyond Neptune. But here's what most people don't realize. When you truly understand why this planet might exist, when you grasp the subtle clues it leaves behind, it changes how you see the outer edge of our solar system. This isn't just another world added to a list. It's a hidden presence, so distant and so elusive that it challenges how we search for anything in deep space. And by the end of this journey, you're going to understand exactly why astronomers are convinced something is out there, and why finding Planet 9 could rewrite what we know about our own cosmic neighborhood. Before we go any further, if you find this kind of deep exploration interesting, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's dive in. Beyond Neptune, the solar system stretches into darkness, a region sparse, cold, and largely unseen. Here lies the Kuiper Belt, a vast ring of icy bodies, dwarf planets, and frozen fragments left over from the early formation of the Sun. These objects are small, distant, and faint, drifting slowly along elongated orbits. They reflect little sunlight, appearing as mere points of light in the most powerful telescopes. Observing them is a task of patience, requiring long exposures and careful tracking. Even with the most advanced instruments, many of these bodies remain hidden, detectable only when they move against the backdrop of distant stars. The Kuiper Belt is not uniform. Some regions are more densely populated, while others are scattered, almost empty. Objects vary in size, from dwarf planets like Pluto, Haumea, and Makemake, to tiny chunks of ice no larger than a city block. Comets occasionally enter the inner solar system from this region, offering brief glimpses of what lies far beyond. Their paths are shaped by gravity, mostly from Neptune, but subtle shifts suggest other forces at play. Observers first noticed these anomalies decades ago when tracking the outermost bodies revealed orbits that did not quite match expectations. Even the largest telescopes can only reveal a fraction of what exists. Many bodies are so dim that they remain invisible until they approach the inner edge of the Kuiper Belt. Distances are immense. Some objects orbit hundreds of times farther from the Sun than Earth does. Light from the Sun reaches them after hours of travel, and reflected light returns faintly, like whispers from the edge of the solar system. Detecting these objects is a matter of interpreting subtle changes in these whispers, noting tiny shifts over months and years. Early discoveries in the outer solar system challenged assumptions. Pluto, discovered in 1930, was the first indication that the solar system extended beyond Neptune. Later, the detection of more distant icy bodies revealed a population of objects with unusual orbits. Their alignment did not match predictions from classical models of planetary motion. Some tilted in ways that were unexpected. Some moved more slowly than expected, hinting at hidden forces shaping their motion. Each new discovery added pieces to a puzzle whose full picture remained unseen. Observing the Kuiper Belt also highlighted the limitations of our perspective. Telescopes survey only small regions of the sky at any given time, and objects moving slowly across vast distances can be missed entirely. The farther an object is, the dimmer it appears, and the harder it becomes to distinguish from background noise. Even the brightest bodies can take years to complete a full orbit, meaning long-term tracking is essential to understand their paths. Dwarf planets in the Kuiper Belt offer particular insight. Pluto, once considered the ninth planet, is now a reference point. Haumea and Makemake show that the outer solar system is home to bodies with unusual shapes and rotations. Haumea spins rapidly, elongated by its motion, while Makemake carries a dark surface punctuated by bright spots, evidence of ice and organic compounds. These characteristics hint at complex histories, collisions, and processes long after the Sun formed. Comets provide another lens into this distant region. When a comet approaches the inner solar system, its icy surface warms and vaporizes, forming a bright tail that can stretch millions of kilometers. These travelers are direct messengers from the Kuiper Belt and beyond, carrying information about the primordial material that formed the planets. Yet, only a fraction of the belt's objects ever make this journey. The rest remain in deep space, quiet and nearly invisible. The distribution of objects in the Kuiper Belt is not random. Some lie in resonances with Neptune, caught in orbital patterns where gravitational influence holds them in place. Others drift in more erratic orbits, suggesting past interactions or unseen influences. These patterns provide clues to the architecture of the solar system and the forces acting beyond Neptune. Even subtle shifts in orbit can signal the presence of something massive, unseen, and distant. Studying these objects demands extraordinary patience. Observers measure positions repeatedly over years, building detailed catalogues of orbits. Brightness, color, and surface composition are recorded when possible. Each new data point refines models and sharpens predictions. But there is always uncertainty. Small errors in measurement or unseen factors can obscure the true motion of these distant bodies. Scientists must weigh evidence carefully, often relying on statistical patterns rather than single observations. Early hints of irregularities set the stage for deeper questions. Some objects appeared to cluster in ways classical physics could not easily explain. Their orbits angled toward a similar region of space. Some were highly elongated, traveling far beyond the bulk of the Kuiper Belt. These patterns could not arise by chance. They suggested a gravitational influence from a massive object lying far beyond what had been catalogued. The very edges of the solar system seemed to bend under a hidden force. Even now, the Kuiper Belt remains only partially mapped. New objects are discovered each year, some only a few kilometers across. Each addition helps trace the contours of this distant region, but also raises more questions. If something massive is influencing these orbits, what is its nature? How far does it extend? What does it mean for our understanding of the solar system? The answers are buried in cold, dark space, waiting for discovery. The outer solar system is a frontier of extremes. Temperatures hover near absolute zero. Sunlight is weak and diffuse. Objects drift slowly, taking centuries or millennia to complete an orbit. Collisions are rare but possible, shaping bodies over eons. Gravity rules this region, subtle yet relentless, dictating the motion of objects across immense distances. Yet even the faintest tug can reveal a hidden presence, a force that hints at something beyond what has been seen. Patterns in the Kuiper Belt's distribution point to a story we have only begun to tell. The clustering of distant objects, the odd tilts, the elongated paths. They whisper of a planet that may exist far beyond Neptune, influencing everything from afar. Observing the belt is like watching waves on a dark ocean. The ripples hint at a current beneath the surface, but the source remains unseen. Every discovery, every measurement, nudges the map of the outer solar system closer to a truth that is both enormous and elusive. As telescopes scan the sky night after night, cameras capture streaks of light moving against the starry backdrop. Each streak could be a small frozen world, a dwarf planet, or a comet. But collectively they tell a story of motion, alignment, and hidden influence. The edges of the solar system are alive with subtle gravitational conversations, silent yet telling. And among these icy bodies there may be one whose presence dominates all the rest, shaping their paths and the architecture of space in ways we have only just begun to understand. The more astronomers observed the distant reaches beyond Neptune, the more patterns emerged. Certain objects, known as extreme trans-Neptunian objects, or ETNOs, moved in ways that seemed deliberate, as if guided by an invisible force. These objects have orbits that are highly elongated, carrying them far from the Sun and then swinging them back close to the solar system. But they do not point in random directions. Instead, many of these orbits cluster toward the same region of space. The clustering is subtle but undeniable. When plotted, the paths of ETNOs form alignments that defy chance. Classical models of planetary motion, which account for Neptune's influence, cannot fully explain why these orbits converge. Some objects tilt at odd angles, some swing in extreme loops, and yet they share a similar orientation. This is not a coincidence. Gravity from the known planets cannot produce this pattern. Something else must be exerting influence, far beyond the reach of Neptune and the rest of the planetary lineup. Astronomers began to examine these patterns in detail. They catalogued dozens of ETNOs, recording positions, speeds, and orbital angles. When the data were analyzed statistically, the results were striking. The odds of this clustering occurring randomly were extremely low. In other words, the evidence pointed toward a hidden force shaping the motion of these distant bodies. Each new discovery reinforced the idea, tightening the web of evidence, but the exact source remained unseen. The anomalies extend beyond alignment. Some ETNOs have orbits that are not just clustered, but also unusually elongated. Their farthest distance from the Sun can be hundreds of astronomical units, well beyond Neptune, while their closest approach brings them nearer, yet still far beyond Pluto. This stretching of orbits cannot arise naturally from interactions with only the known planets. It implies the gravitational pull of a massive, unseen body, tugging gently but persistently over millions of years. Further peculiarities appear when examining the inclination of these objects. Many are tilted significantly from the plane in which the main planets orbit. These inclinations are not random. They hint at a force that is not simply pushing in one direction, but shaping trajectories in a consistent, coherent pattern. Even subtle gravitational nudges over long periods can bend an orbit, and when multiple bodies show similar distortions, the signal becomes clear. Scientists compared the distribution of ETNOs to models of random motion. Using simulations, they recreated billions of potential orbital paths under the influence of only known planets. None matched the observed clustering. The statistical confidence that a massive, distant perturber exists increased with each object tracked. In practical terms, this means there is more than a 99% chance that the arrangement of these objects is not accidental. Gravity is whispering the presence of something far away, something powerful enough to shape the architecture of the outer solar system. The pattern is reinforced by what some call the anti-aligned objects. These bodies have orbits that point roughly opposite to the clustered group, yet their paths are also unusual and influenced by a hidden mass. Together, the aligned and anti-aligned etnos suggest a massive planet moving on a slow, distant orbit, exerting a long-range gravitational pull that organizes orbits across hundreds of astronomical units. Even the smallest bodies in the extreme outskirts provide clues. Tiny, icy rocks, far dimmer than Pluto, show similar orbital behaviors. Their positions, when compared statistically to the larger objects, support the same story. An unseen influence directing the outer solar system like the hand of a puppeteer, though it is thousands of times farther from the Sun than Earth. Observational bias was considered. Could it be that telescopes are only seeing objects in certain directions, creating a false pattern? Researchers accounted for this, modeling survey coverage and selection effects. After corrections, the clustering remained. The pattern was real, not an artifact of observation. The solar system, as observed, is shaped by something massive and distant, unseen but undeniably present in its gravitational fingerprints. The properties of this hypothesized body began to take shape. For the orbital patterns to exist, the object must be several times the mass of Earth. It must follow a highly elongated orbit, tilted relative to the plane of the known planets. Its distance could range from hundreds to over 1,000 astronomical units at aphelion, placing it far beyond the reach of current telescopes. The characteristics inferred from orbital dynamics form a portrait of a world hidden in shadow, a massive planet shaping the motion of countless icy bodies from afar. Simulations revealed more. The predicted planet would shepherd etnos into their observed alignments over millions of years. Without it, the orbits would scatter, randomizing over time. The existence of the pattern today implies stability caused by a gravitational anchor consistent with a large, distant planet. This insight transformed the search from speculative curiosity to a focused scientific endeavor, with astronomers combing the sky along the predicted orbit paths. The more etnos were discovered, the more the invisible influence was mapped indirectly. Each addition refined models, narrowing the possible locations of the unseen planet. Astronomers now had a target zone, a swath of the sky where Planet 9 might lie. Observational campaigns were organized with patience and precision, knowing that any detection would confirm years of gravitational detective work. These orbital clues also raised broader questions. Could other massive bodies exist in the outer solar system? Was Planet 9 unique, or a survivor of a larger population that formed during the early solar system? The presence of a single massive perturber explained current observations. But the door opened to the possibility that the solar system's outskirts were more complex than previously thought. The study of etnos transformed the outer solar system from a cold, empty region into a laboratory for gravity. Each icy object acts as a tracer, mapping invisible forces over unimaginable distances. The evidence points consistently toward one conclusion. A massive, distant body exerts a gravitational pull strong enough to organize orbits across hundreds of astronomical units. The outer solar system is not random. It is structured, shaped, and held in place by something unseen. Astronomers now faced the challenge of linking prediction to observation. The orbital anomalies were compelling, but nothing had been directly seen. The alignment of ETNOs provided a map, an indirect signature of Planet Nine's presence. Following this map required patience, technology, and a willingness to look where light was almost gone. Every observation added weight to the gravitational story, building a portrait of a world that, so far, has evaded detection. By studying these orbits in detail, scientists could estimate more than just the existence of Planet Nine. They could infer its mass, its tilt, and the shape of its orbit. They could model its influence over millions of years, showing how it shepherded ETNOs into their observed positions. The patterns were a fingerprint, invisible but real, offering the first tangible evidence that a new planet might lie beyond the known edge of the solar system. The clues hidden in the orbits are subtle, persistent, and undeniable. They tell a story of motion across vast distances, of gravity shaping the outer solar system in ways classical models cannot explain. The more researchers study these bodies, the stronger the evidence grows. And yet, the planet itself remains unseen, a shadow lurking at the edge of light, waiting to be found, confirming the gravitational whispers etched into the paths of distant icy worlds. In 2016, two astronomers, Konstantin Batygin and Mike Brown, published a paper that would capture the attention of the scientific world. They had analyzed the orbits of extreme trans-Neptunian objects, the distant icy bodies whose paths seemed to cluster in ways that defied known physics. Their work suggested a simple but extraordinary conclusion. Something massive was influencing these orbits, something unseen yet undeniably present. Batygin and Brown's calculations indicated a planet several times the mass of Earth. They proposed a body with a highly elongated orbit, tilted relative to the plane of the known planets. At its closest approach to the Sun, it might be hundreds of astronomical units away. At its farthest, the distance could stretch to more than 1,000 times the space between Earth and the Sun. Its orbit would take thousands of years to complete, moving slowly across the sky, almost imperceptibly to observers on Earth. The idea of Planet Nine was at once simple and revolutionary. It offered a clear explanation for the clustering of ETNOs, the tilts of distant orbits, and the elongated paths of objects at the edge of the solar system. Yet, it was also controversial. Nothing of this planet had been directly observed. Its existence rested entirely on indirect evidence and mathematical modeling. This was a new approach, relying on patterns in motion rather than the traditional method of seeing a body through a telescope. The predicted characteristics of Planet Nine were specific. Its mass would likely be between 5 and 10 times that of Earth, placing it between Earth and Neptune in size, but much colder and more distant. Its orbit would be elongated, with an eccentricity much higher than any known planet, and inclined at an angle of roughly 30 degrees to the plane of the solar system. These parameters were not arbitrary. They emerged directly from simulations designed to match the observed distribution of ETNOs. Batygin and Brown ran thousands of simulations, adjusting mass, distance, and orbital tilt to see which combination would reproduce the orbital alignments of distant bodies. The models consistently required a massive object far beyond Neptune. Without it, the orbits would be scattered randomly over time. With it, the ETNOs settled into the observed configuration, stable over millions of years. The match was precise, compelling, and hard to ignore. Scientific debate erupted immediately. Some astronomers questioned whether the clustering was real or the result of observational bias. Could the way telescopes surveyed the sky create a false signal? Others asked if the orbits could be shaped by collective gravitational effects of smaller bodies rather than a single massive planet. Skeptics pointed to alternative explanations, reminding the field of past claims that had not been confirmed. Battigan and Brown welcomed this scrutiny. They refined their models, incorporating more etnos and testing sensitivity to various assumptions. Each refinement strengthened the case, but the debate remained open. The hypothesis of Planet 9 was not yet a discovery. It was a prediction, backed by robust mathematical reasoning and observable consequences, but awaiting confirmation through direct detection. The search for Planet 9 became a global endeavor. Astronomers began focusing telescopes on regions of the sky indicated by the simulations. Because the predicted orbit is so distant and slow, sightings would be rare and faint. Even the largest ground-based telescopes might struggle to detect it. Observers had to scan wide areas methodically, capturing faint light over multiple nights and tracking motion across months and years. Patience was essential, and certainty remained distant. The predicted orbit of Planet 9 suggested it would spend most of its time far from the Sun, in darkness, cold, and isolated. At these distances, sunlight is so weak that the planet would be extremely dim, reflecting almost no light. Detection required both wide surveys and long exposures, often using the most sensitive cameras available. Any hint of motion in the expected region could signal a monumental discovery. Alternative explanations persisted. Some researchers proposed that a disk of small, icy bodies beyond Neptune could generate similar orbital patterns through collective gravity. Others suggested that past encounters with rogue planets or passing stars could have shaped the etnos temporarily. While plausible, these scenarios struggled to match the observed alignment as consistently as a single massive planet could. The gravitational signature of Planet 9 remained the most elegant and predictive explanation. The hypothesis also sparked speculation about the planet's origin. How did it arrive in such a distant and tilted orbit? One idea suggested it formed closer to the Sun and was later scattered outward through interactions with Jupiter or Saturn during the solar system's early chaotic phase. Another possibility was that it formed where it currently resides, accreting slowly in the cold outer reaches of the protoplanetary disk. Regardless of its origin, the gravitational influence it exerts today is observable in the motion of etnos. Simulations continued to improve as new objects were discovered. Each addition to the catalogue of extreme trans-Neptunian objects refined predictions for the planet's orbit. With more data, astronomers could narrow the regions of the sky most likely to host Planet 9. The models became dynamic, adjusting in real time as discoveries were made, and offering a roadmap for targeted searches with telescopes capable of detecting faint light in the far reaches of space. The predicted characteristics of Planet 9 also raised intriguing questions about the rest of the solar system. Could its gravitational influence extend to the inner edge of the Kuiper belt? Might it occasionally perturb comets, sending them toward the inner solar system? Could it affect the orbits of distant dwarf planets, or even the Oort cloud far beyond? Each question highlighted the interconnectedness of the solar system and the subtle power of a massive, distant world. Skepticism remained healthy. No single line of evidence could confirm Planet Nine's existence. The hypothesis relied on the coherence of multiple orbital anomalies and their statistical improbability. Observational bias, alternative gravitational explanations, and the possibility of yet unseen forces kept the scientific community cautious. Still, the pattern was consistent, reproducible, and compelling. Batygin and Brown's work transformed the outer solar system into a realm of inquiry and suspense. The idea of Planet Nine shifted from speculation to testable science. It was no longer a vague notion of a distant planet. It was a hypothesis with specific predictions, measurable consequences, and defined search regions. Observers now had a target, a shadow to chase across billions of kilometers of space. The hypothesis also reshaped the imagination of astronomers and the public alike. For centuries, the solar system was thought to be largely understood, a neatly ordered arrangement of planets with minor debris beyond Neptune. Planet Nine suggested that our knowledge was incomplete, that hidden worlds could lurk in the cold, distant darkness, influencing the motion of countless objects silently over eons. Every aspect of the Planet Nine hypothesis was grounded in evidence. From the alignment of etnos to the statistical models and simulations, the work provided a roadmap for both observation and verification. It was a blueprint for discovery, a plan to locate an invisible architect of the outer solar system. Yet, despite its promise, the planet remained unseen, teasing astronomers with indirect proof and leaving a question hanging over the entire endeavor. Could we detect it before it slipped further into darkness? Or would this massive world remain a shadow on the edge of knowledge indefinitely? Even with precise predictions, finding Planet Nine is far from simple. It is extremely distant, far beyond the reach of ordinary telescopes. The sunlight reaching it is weak, diffused over billions of kilometers, and what little light it reflects returns to Earth faint and almost invisible. Any direct view of this planet requires instruments capable of detecting near-invisible points against the dense backdrop of stars. The farther it is, the slower it appears to move. Night after night, its motion is barely perceptible, making it easy to confuse with background objects. Tracking it requires patience, measured in months and years. Telescopes face natural limits. Even the largest ground-based observatories have narrow fields of view relative to the vast sky. Searching for Planet Nine is like looking for a single drop in an ocean of stars. Observers must cover large regions systematically, scanning and rescanning to ensure faint light sources are not overlooked. Long exposure times are necessary to collect enough photons to register the planet, but too long an exposure risks blurring its motion. Strategies must balance coverage, sensitivity, and timing, a delicate equation where failure is easy and success demands precision. Optical telescopes rely on reflected sunlight, but at distances of hundreds of astronomical units, the brightness of Planet Nine would be hundreds of thousands of times fainter than Pluto. Even if it were relatively large, its apparent magnitude would place it beyond casual detection, often blending with the background noise of faint stars. In contrast, infrared telescopes look for heat rather than reflected light. Although Planet Nine is extremely cold, it radiates its internal heat, providing a faint signature detectable in the infrared spectrum. Yet these surveys face their own challenges. Thermal signals are weak, and the sky itself emits infrared radiation, creating interference that must be filtered and corrected. Past sky surveys have scanned for distant planets, often without success. Projects like the Wide Field Infrared Survey Explorer, WISE, catalogued billions of objects, yet Planet 9 remained elusive. This absence does not rule out its existence. The predicted orbit covers regions of sky that may have been lightly surveyed or overlooked due to observational limitations. Even if a planet passes through surveyed areas, its slow motion can make it difficult to distinguish from stationary stars. Detecting movement over long intervals is key, requiring repeated imaging over years. Ground-based surveys continue to expand. Large telescopes such as the Subaru Telescope in Hawaii or the Cerro Tololo Inter-American Observatory in Chile combine wide-field imaging with deep sensitivity. By taking multiple images over months, astronomers can track faint objects as they shift slowly across the star field. Any candidate moving consistently along a predicted path could signal the presence of Planet 9. Verification demands further observation and careful elimination of false positives caused by background galaxies, distant stars, or instrument artifacts. Observing from space offers distinct advantages. Telescopes outside Earth's atmosphere avoid atmospheric turbulence, light pollution, and weather interference. The Hubble Space Telescope and other space-based observatories have contributed to cataloguing distant objects, but their narrow fields make wide-area searches slow and inefficient. Large surveys optimized for faint, distant sources are essential. Coordination between ground and space observations increases the chance of detection by cross-referencing candidates in different wavelengths. The planet's predicted motion complicates detection. Near aphelion, when it is farthest from the Sun, Planet 9 would move extremely slowly, appearing almost fixed over the course of weeks or months. This slow motion requires patience and long-term planning. Observers must compare images separated by long intervals to detect subtle shifts. Rapid surveys might miss it entirely, dismissing it as background noise. Each survey must account for the unique combination of faintness, distance, and slow apparent movement. Infrared versus optical detection illustrates complementary strategies. Optical surveys are effective when the planet is closer to the Sun, reflecting more light, but the farther it drifts, the weaker the signal. Infrared surveys can detect residual heat, even at extreme distances, but sensitivity is limited by the thermal noise of the telescope and the sky. Both approaches are necessary, and each provides partial information. Combined, they enhance the probability of eventual detection. Survey strategies also consider orbital predictions. Models from Batygin and Brown suggest specific regions where Planet 9 is most likely to appear. Telescopes are targeted along these predicted paths, maximizing efficiency. Observers prioritize areas where the alignment of ETNOs indicates the planet's gravitational influence is strongest. This guided approach increases the likelihood of finding the planet compared to random sky sweeps, yet the search remains daunting due to the vastness of space and the faintness of the object. Astronomers also rely on serendipity. Some distant objects were discovered while surveying unrelated regions. Occasionally, objects appear unexpectedly, providing clues about the planet's presence. These chance discoveries help refine models and guide subsequent searches. Patience and persistence are essential. The planet may be hiding in a corner of the sky already captured in past images, awaiting careful re-examination to reveal its presence. The technical challenge is compounded by competing priorities. Telescopes capable of detecting Planet 9 are also used for other research, from studying nearby stars to mapping distant galaxies. Allocating observation time requires careful justification. Each night spent searching for a faint, unseen planet represents a commitment to a long-term pursuit, where immediate results are rare and the payoff could take years. Even after detection, verification is difficult. Multiple observations are needed to confirm motion and orbit. False positives can arise from instrument errors, variable stars, or distant galaxies. Candidate objects must be tracked repeatedly over months to establish a consistent orbit. Only then can astronomers claim the planet has been found. Until that point, every candidate is provisional, a tantalizing hint that must survive rigorous scrutiny. The search for Planet 9 is not only a scientific challenge, but a logistical one. Coordinating international surveys, processing massive amounts of data, and maintaining patience over decades are all necessary. Observers must remain vigilant for faint signals that shift imperceptibly across billions of kilometers. Each survey, whether in optical or infrared, contributes pieces to a larger puzzle, a map of the outer solar system waiting to reveal a hidden architect. Despite these challenges, the potential reward is enormous. Detecting Planet 9 would confirm predictions made from gravitational clues, validate models of the outer solar system, and expand our understanding of planetary formation. It would mark the first discovery of a massive planet in the solar system in nearly 170 years. The difficulty of detection only magnifies the significance. A world so distant and faint, yet exerting measurable influence on distant icy bodies, would reshape the map of our solar system and the boundaries of human knowledge. As surveys continue, astronomers refine search techniques. Algorithms filter billions of data points to identify potential candidates. Automated systems flag objects that move consistently over time. Observers review these candidates with careful scrutiny, comparing positions, brightness, and motion across multiple wavelengths. This process is slow but necessary, ensuring that any claimed discovery is real and reproducible. The vastness of the sky and the dimness of the planet make the search a challenge in extremes. It requires long-term commitment, sophisticated technology, and careful interpretation of faint signals. Yet every year, new surveys increase the probability of detection. Each new extreme trans-Neptunian object discovered improves orbital models, narrowing the regions where Planet 9 might reside. Observation, prediction, and refinement form a continuous loop, slowly closing in on a planet that remains unseen, but whose gravitational footprint is unmistakable. The challenges of direct observation are immense, yet each difficulty highlights the subtlety of the clues astronomers follow. Faint light, slow motion, extreme distance, all combine to hide the planet, while its influence whispers through the paths of ethnos. Detecting Planet 9 is not impossible, but it is a test of patience, technology, and persistence. The outer solar system offers a silent hunt, a chase across billions of kilometers, where success depends on seeing what is almost invisible, following motion measured in millimeters across the sky, and trusting the signals written in the orbits of distant icy worlds. If Planet 9 exists, its influence extends far beyond a simple orbit. Gravity is invisible, yet undeniable. Even at hundreds of astronomical units from the Sun, a planet of several Earth masses exerts a pull that subtly shapes the motion of countless distant bodies. The orbits of extreme trans-Neptunian objects, already unusual, are held in place and aligned by this gravitational presence. The very architecture of the outer solar system depends on these quiet, persistent forces. The Kuiper belt is especially sensitive to such distant influence. Objects in its outer edge follow paths that appear almost choreographed. Without Planet 9, models suggest their orbits would scatter, randomizing over millions of years. Instead, the clustering observed today implies long-term stability, maintained by a massive perturber. Even bodies that seem isolated feel the tug, their trajectories nudged gently over eons, shaping the overall distribution and tilt of the belt. Comets also respond to distant gravity. Most comets originate in the Kuiper belt, or the more distant Oort cloud, a vast shell of icy bodies surrounding the solar system. A planet as massive as Planet 9 could alter the paths of comets, changing how and when they travel toward the inner solar system. Some may be shepherded into more elongated orbits, while others are deflected into regions where encounters with other bodies become more likely. Over millions of years, the planet's pull subtly redirects countless small objects across the frozen outskirts. The Oort cloud, extending thousands of astronomical units from the Sun, lies at the frontier of gravitational influence. Planet 9 would not dominate the region, but its pull could trigger long-range effects. Comets from the inner Oort cloud may feel slight perturbations, nudged just enough to alter trajectories. While these forces are minor, cumulative effects over eons create measurable patterns in the distribution of distant icy objects. The planet acts as a hidden sculptor, carving structure in a realm we can barely observe. Planet 9's influence is not only structural, but also dynamic. Its presence introduces resonances, regions where orbits stabilize or destabilize due to periodic gravitational effects. Objects captured in these resonances experience subtle but consistent shifts. Their orbital periods and angles adjust to accommodate the massive planet. These resonances create zones of accumulation and avoidance, producing the distinct clustering of ETNOs observed today. Patterns that once seemed random now reveal an underlying order. Simulations of the solar system with Planet 9 show that its orbit is a key factor in shaping the outer solar system's evolution. Even at great distances, a planet with sufficient mass can alter the eccentricity and inclination of distant bodies. Over millions of years, the belt's outermost objects adopt specific orbital alignments, as if following invisible rules. This long-term sculpting is slow but persistent, subtle enough to avoid notice in short-term observations, yet powerful across geological timescales. The implications for planetary formation are profound. Traditional models suggest that planets form within the protoplanetary disk, close to the Sun, where material density is sufficient for accretion. A planet at extreme distance challenges these ideas. Did it form in place, where matter was sparse and temperatures frigid, or was it scattered outward after formation closer in? Either scenario alters our understanding of planetary growth and migration. Planet 9 may be evidence of processes we have never observed directly, offering a window into the history of our solar system. The planet's orbit may also provide insight into the early solar system's dynamics. If it was scattered outward by interactions with Jupiter or Saturn, It suggests a chaotic phase where planets influenced each other dramatically, reshaping the distribution of matter. If it formed in situ, accretion could occur even in cold, low-density regions, challenging assumptions about where planets can develop. Its gravitational influence, observable today, carries the memory of these ancient events. Planet Nine's presence offers a natural explanation for previously puzzling features. Some detached objects with orbits that seem disconnected from Neptune now make sense as responses to a distant mass. Certain high-inclination bodies, tilting dramatically relative to the ecliptic, are shaped by resonances with the unseen planet. The outer solar system emerges not as chaotic or random, but as a structured, predictable environment, influenced by both visible and invisible forces. Gravitational interactions extend beyond orbital alignment. Over long periods, Planet Nine can induce slow changes in eccentricity, gradually stretching or compressing orbits. Even minor shifts accumulate over millions of years, creating the elongated paths observed in extreme trans-Neptunian objects. The cumulative effect of a distant planet is subtle yet profound, revealing that even in the darkest reaches, order is maintained by invisible hands. Comets entering the inner solar system carry indirect evidence of distant influences. Their approach angles and velocities reflect perturbations from objects far beyond Neptune. A massive Planet Nine can deflect their paths, sending some closer to Earth or redirecting them to more distant orbits. The interplay between inner and outer solar system bodies illustrates how gravity operates over vast scales, linking distant icy worlds to the dynamics of the entire planetary system. Planet Nine's gravity may also help explain the existence of extreme orbits that are otherwise unstable. Objects with long-period, high-inclination paths survive because of the stabilizing effect of a distant mass. Without such a planet, simulations predict these orbits would become chaotic, with objects scattered or ejected from the solar system. The hypothesized planet provides a simple explanation for the persistence of unusual orbits that have puzzled astronomers for decades. The presence of a distant massive planet informs predictions for future discoveries. If Planet Nine exists, newly discovered extreme trans-Neptunian objects should follow specific patterns, aligning with the planet's orbit or resonances. This predictive power transforms the search from guesswork to a focused scientific method. Observers can target regions with the highest likelihood of revealing additional evidence, gradually mapping the influence of a hidden giant. Beyond the solar system, the concept of Planet Nine influences how astronomers understand other planetary systems. Observations of distant stars often reveal giant planets on eccentric or tilted orbits. Our own solar system, with a massive, distant planet, may not be unusual. The outer solar system becomes a laboratory for understanding planetary dynamics across the galaxy, showing how unseen forces sculpt systems over billions of years. Planet Nine also prompts reconsideration of mass distribution in the solar system. While inner planets dominate the familiar plane, the outer reaches may contain more mass than previously thought, influencing long-term dynamics. Even a single planet of several Earth masses exerts a disproportionate effect, reshaping the architecture of objects far beyond Neptune. Its gravitational footprint extends silently, structuring the outskirts in ways classical models cannot account for. The broader consequences extend to long-term stability. A massive outer planet can regulate the scattering of comets and minor bodies, protecting inner planets from catastrophic collisions or channeling icy objects into the Oort cloud. It serves as a distant sentinel, its presence influencing both the structure and evolution of the solar system. The faint, cold planet acts as an unseen guardian, shaping space from afar. Planet Nine's gravity demonstrates the subtle power of long-range forces. Objects feel its pull without direct contact. The patterns of extreme trans-Neptunian objects, the alignment of high-inclination bodies, and the shape of distant orbits all reflect this influence. The consequences are measurable, observable, and reproducible through simulations. Gravity, though invisible, writes a story across billions of kilometers, revealing a system shaped not only by visible planets, but by hidden giants in the dark. Studying these effects informs our understanding of solar system formation. It emphasizes that the outer solar system is active, structured, and influenced by forces we cannot see directly. Each orbit, each alignment, each subtle nudge of a distant object is a record of gravitational interaction, echoing over millions of years. Planet Nine, if real, demonstrates that even the farthest reaches of the solar system are part of a connected, dynamic system, a cosmos where hidden influence governs structure in silence. The cosmic consequences of Planet Nine, therefore, are profound. Its gravity organizes the outskirts, guides the motion of icy bodies, and preserves extreme orbits. It potentially directs the paths of comets and shapes the distant Oort cloud. It challenges planetary formation theories and highlights the complexity of our solar system. A hidden world at the edge of light can dictate motion across billions of kilometers, leaving fingerprints in the cold, dark expanse of space. The outer solar system is not empty. It is alive with patterns sculpted over time by forces both visible and invisible. The search for distant, unseen planets is not new. More than a century ago, astronomers looked beyond known worlds for evidence of a Planet X, a hypothetical body thought to explain anomalies in Uranus and Neptune's motion. These early efforts were guided by observation, calculation, and hope. They relied on careful tracking of planetary positions, noting discrepancies, and searching the sky for something massive that might account for the differences. The discovery of Neptune in 1846 is one of the most famous successes of such prediction. Astronomers noticed that Uranus deviated from expected paths. Using mathematics and Newton's laws, they calculated where a new planet must be to cause these shifts. Telescopes were directed toward that region, and Neptune appeared as a faint point of light. This achievement demonstrated the power of indirect evidence. Even without seeing the planet directly at first, its gravitational effects revealed its existence. After Neptune, the search for other hidden planets continued. Astronomers proposed a Planet X beyond Neptune, intending to explain residual orbital irregularities. Some believed a massive body must exist to stabilize the outer solar system. Over decades, telescopic surveys and photographic plates were used to scan large portions of the sky. Each lead was followed, each anomaly studied, yet the results were often inconclusive. Some predictions were based on incomplete data, others on measurement errors. Many supposed discoveries vanished upon further scrutiny. These past false leads taught valuable lessons. Observations are subject to error, and celestial mechanics are complex. What appeared to be unexplained perturbations could arise from minor inaccuracies in data or unknown influences within the solar system. Scientific persistence, however, allowed astronomers to refine methods, cross-check measurements, and distinguish signal from noise. Each mistake contributed to the development of more rigorous approaches. The history of Planet X searches highlights the need for patience, meticulous analysis, and an openness to being wrong. Technological limitations in the past made detection difficult. Telescopes were smaller, photographic plates less sensitive, and the sky vast. Scanning required physical effort, moving plates, inspecting thousands of images manually, often with faint targets lost amid countless stars. Modern searches benefit from digital imaging, automated detection algorithms, and sensitive wide-field surveys. These advances allow astronomers to cover far more sky with greater precision, identifying faint moving objects that would have been invisible a century ago. The story of Pluto illustrates both the promise and challenge of hidden planets. In 1930, Clyde Tombaugh discovered Pluto while searching for Planet X. Initially thought to be massive enough to explain Uranus's motion, it later became clear that Pluto was too small to account for the discrepancies. Nevertheless, the discovery demonstrated that systematic sky surveys could reveal unexpected worlds. Pluto also highlighted the limits of indirect prediction. Not every anomaly corresponds to a large planet, and some leads may reveal smaller, unforeseen objects instead. Historical searches relied on manual comparison of photographic plates taken weeks or months apart. Observers had to identify tiny motions, faint shifts against the backdrop of fixed stars. In contrast, modern surveys employ software to automatically detect movement, quantify brightness, and flag potential candidates for follow-up. Long-term observation campaigns now use precise telescopes capable of detecting extremely faint light at infrared and optical wavelengths, allowing astronomers to track objects thousands of times fainter than what early observers could see. Past efforts also showed the importance of statistical analysis. Discrepancies in planetary positions could be misinterpreted as evidence of a hidden planet. Only by analyzing patterns across many observations, accounting for observational errors and biases, could meaningful predictions be made. Modern techniques use computer simulations to test hypotheses, modeling how a distant planet would influence the orbits of thousands of objects over millions of years. These methods provide a level of precision and confidence impossible in earlier eras. Lessons from history also shape expectations. Some hypothesized planets vanished from consideration after more data became available. Skepticism and verification are necessary components of discovery. Planet 9 follows this tradition. Its existence is proposed not because a single object is observed directly, but because consistent patterns emerge from multiple extreme trans-Neptunian objects. Historical experience reminds astronomers that indirect evidence must be interpreted carefully, verified repeatedly, and tested against alternative explanations. The contrast between past and present searches is striking. Early efforts relied on small telescopes, limited fields, and manual inspection. Modern astronomy uses sensitive instruments, vast data storage, and automated analysis. Infrared surveys can detect objects by heat rather than reflected light, while optical surveys capture faint glimmers of sunlight. Together, these techniques allow comprehensive coverage of predicted regions, dramatically increasing the likelihood of discovery. The search for Planet 9 is informed by centuries of planetary exploration. From Uranus and Neptune to Pluto and beyond, astronomers have learned to combine mathematics, observation, and patience. Each success and failure contributes to a cumulative understanding of how to hunt for worlds that are faint, distant, and slow-moving. The history of hidden planets is not a story of error alone, but of gradual refinement of technique, analytical rigor, and resilience in the face of uncertainty. Even failed predictions have value. They illuminate the limits of observation and calculation, highlighting where assumptions or data were incomplete. By understanding past mistakes, modern astronomers design more effective surveys, choose better instruments, and apply more sophisticated modeling. The legacy of historical searches is a roadmap for tackling the extreme challenges of discovering a massive planet in the outer solar system. The concept of Planet 9 stands on the shoulders of these past searches. It represents a continuation of a long tradition, using gravitational clues to reveal unseen worlds. Unlike previous searches, it benefits from digital technology, powerful telescopes, and extensive computational models. Observations are guided by specific predictions rather than chance, focusing resources on regions where the planet is most likely to reside. This approach increases efficiency and provides a clear path for testing the hypothesis. Historical context also emphasizes scientific patience. Planets are discovered slowly, often taking years or decades of observation. Modern astronomers expect the same for Planet 9. Even with the best technology, the sky is vast, and faint objects move slowly. Verification requires repeated observations, careful analysis, and long-term commitment. The outer solar system does not yield its secrets quickly, and patience is a prerequisite for success. Ultimately, understanding the past prepares astronomers for the future. The discovery of Neptune, the search for Planet X, the unexpected find of Pluto, and numerous false leads have all contributed to methods used today. Planet 9 is part of this continuum, each modern challenge that applies lessons learned over centuries. Indirect evidence, statistical modeling, and systematic surveys build on the cumulative knowledge of generations, blending human persistence with technological precision. By examining historical searches, astronomers can anticipate pitfalls and refine strategy. They recognize that anomalies can mislead, observations can deceive, and patterns can be coincidental. The difference today is computational power, advanced imaging, and predictive models. Modern techniques transform speculation into testable hypotheses, allowing the search for Planet 9 to proceed with rigor, guided by both the past and the possibilities of present technology. The history of hidden planets also highlights the importance of collaboration. Observations from multiple telescopes, often spread across the globe, are necessary to confirm faint motion. Historical efforts relied on individual astronomers scanning plates. Modern searches use coordinated teams, sharing data, comparing findings, and verifying results. This global approach accelerates discovery while reducing the chance of error that plagued earlier attempts. In this context, Planet 9 is not just a scientific puzzle, but a continuation of a human endeavor spanning centuries. The search connects past techniques with modern methods, blending observation, calculation, and patient scrutiny. It illustrates the evolution of astronomy, showing how mistakes, false leads, and incremental improvements contribute to the possibility of discovering a massive, distant world. The outer solar system is now understood not as empty space, but as a frontier where the invisible can be inferred, modeled, and eventually observed. History reminds us that discovery is rarely immediate. Neptune, Pluto, and other distant bodies required meticulous work over years. Planet 9 demands the same rigor, a methodical pursuit guided by patterns, prediction, and increasingly sophisticated technology. Observers follow a trail left in the orbits of icy bodies, trusting that gravity's invisible hand points to a tangible, if unseen, destination. Each historical lesson reinforces the approach, shaping expectations and strategy, and preparing astronomers for the challenge that lies ahead. Even as the Planet 9 hypothesis gained attention, astronomers considered other possibilities. The patterns in extreme trans-Neptunian objects could have explanations that did not involve a massive hidden planet. One idea is the concept of a self-gravitating disk. If the outer solar system contains countless small icy bodies, their combined gravity might influence each other, producing apparent clustering. A dense disk of objects could, in theory, create the orbital alignments observed without requiring a single dominant planet. Simulations of self-gravitating disks show that such arrangements can produce some degree of clustering, but they also reveal limitations. The number of objects and their mass must be finely tuned. Too few bodies, and the pattern disappears. Too many, and the system becomes unstable. While intriguing, this explanation struggles to account for the precise, consistent alignment observed in extreme trans-Neptunian objects. It remains a possibility, but one that requires improbable conditions. Observational bias is another potential factor. Surveys of the outer solar system are not uniform. Telescopes cover only portions of the sky, and some regions are observed more frequently than others. As a result, the apparent clustering of distant objects might reflect where astronomers look, rather than an underlying gravitational influence. Certain regions are easier to survey due to weather, telescope location, or time allocation. Bias can create the illusion of alignment, when, in fact, objects are distributed more randomly. Addressing observational bias requires careful statistical analysis. Researchers simulate survey coverage, factoring in which areas of the sky have been observed and how faint an object can be detected. When these biases are accounted for, the clustering remains significant, though slightly weaker. This strengthens the case for a real gravitational cause. Observational bias alone cannot fully explain the patterns, leaving room for a massive, unseen planet to exert influence. Rogue planets offer another alternative. A wandering planet captured by the Sun's gravity long ago or passing nearby could perturb distant objects. Such encounters could reshape orbits temporarily, producing clusters of extreme trans-Neptunian objects. Rogue planets are rare, and their effects would diminish over time. For the observed alignments to persist over millions of years, a long-term influence is necessary. A passing planet might explain anomalies in individual objects, but it cannot account for the sustained structure seen today. Other gravitational explanations have been proposed as well. Some suggest that multiple small bodies, collectively influencing extreme objects, could produce similar orbital effects. Others examine the possibility of past interactions with nearby stars, which might have nudged outer solar system objects into unusual paths. These scenarios are plausible in principle, but difficult to reconcile with the precise alignment and long-term stability observed. Each alternative faces challenges when tested against detailed simulations. The complexity of the outer solar system makes ruling out alternatives difficult. Objects are distant, faint, and move slowly. Small errors in measurement or modeling can produce misleading results. Simulations must account for the mass, distance, and orbits of countless bodies, while also incorporating the gravitational influence of known planets. The scale of the system and the timescales involved complicate every hypothesis, whether it proposes a massive planet or a more distributed cause. Planet 9, however, consistently provides the most straightforward explanation. Its presence accounts for both the clustering of extreme trans-Neptunian objects and the tilts of high-inclination bodies. Simulations incorporating a massive distant planet reproduce observed orbits with remarkable precision. Other explanations can produce partial effects, but only a single, massive perturber matches all observed features. The planet's predicted mass, orbit, and tilt explain the patterns naturally, without requiring finely tuned conditions. The predictive power of Planet 9 strengthens its case. Astronomers can use its hypothesized orbit to predict where new extreme objects should be found. Observations increasingly confirm these predictions, revealing additional aligned bodies. Alternative explanations do not offer comparable foresight. A self-gravitating disk or past rogue encounter may explain what is already known, but cannot reliably forecast where new discoveries should occur. Planet 9 also explains multiple features simultaneously. The alignment of orbits, the clustering of angles, and the presence of high-inclination objects all follow naturally from the gravitational influence of a distant planet. Other hypotheses tend to account for one feature while leaving others unexplained. The ability of Planet 9 to unify diverse observations under a single mechanism makes it compelling. Simulations show that, with the planet in place, the outer solar system evolves into the structure we observe today. Researchers continue to test alternatives rigorously. They simulate disks of small bodies with different masses, track the effect of passing stars, and examine possible observational biases in great detail. Each scenario is compared to the observed distribution of extreme trans-Neptunian objects. While some alternatives partially reproduce patterns, none fully account for all features with the simplicity and predictive power of a massive, distant planet. Observational limits make conclusions provisional. Planet 9 remains unseen, so every hypothesis is constrained by indirect evidence. Still, the convergence of multiple lines of analysis, from statistical studies, simulations, and patterns in ethnos, points toward a consistent explanation. A single, massive planet remains the hypothesis that best accounts for the totality of evidence. Its predicted properties match observed anomalies, and its existence provides a framework for future discoveries. The planet's influence also extends beyond orbital clustering. Its predicted orbit shapes long-term dynamics, stabilizes extreme objects, and may influence comet paths toward the inner solar system. No alternative scenario reproduces this wide-ranging effect. Self-gravitating disks, observational bias, and rogue planets can explain fragments, but the unifying mechanism requires a planet exerting continuous, measurable gravity over billions of kilometers. Each alternative serves as a test of the Planet 9 hypothesis. By examining self-gravitating disks, simulating rogue encounters, and modeling survey biases, astronomers stress-test predictions. When these alternatives fail to account for the data fully, confidence in the planet hypothesis grows. Scientific rigor demands consideration of all possibilities, yet evidence accumulates toward the simplest explanation that aligns with observed reality. Planet 9 also integrates historical knowledge. Just as Neptune was predicted from Uranus's motion, this planet emerges from patterns in distant orbits. The search relies on gravity's subtle fingerprints rather than direct observation alone. Unlike past false leads, the hypothesis provides specific predictions, guiding observers to regions of the sky where the planet may appear. Its predictive capacity distinguishes it from alternative ideas that rely on statistical coincidence or temporary phenomena. The hypothesis does not ignore complexity. Models include the influence of Neptune, Uranus, and other known planets, along with perturbations from minor bodies. Simulations explore millions of years, showing how extreme objects evolve under Planet 9's pull. The patterns match observed ethno-alignments across time, suggesting a persistent, long-term influence that alternatives cannot replicate. The planet is not an ad hoc solution, but a requirement emerging naturally from the data. As more extreme trans-Neptunian objects are discovered, simulations continue to refine the planet's predicted orbit. Each new object tests alternatives while enhancing the predictive framework. Self-gravitating disks or random alignments cannot reliably anticipate where future discoveries will appear. Planet 9, however, allows astronomers to forecast positions, refine observational campaigns, and track progress systematically. The hypothesis remains falsifiable, testable, and grounded in measurable reality. Ultimately, alternative explanations highlight the caution inherent in science. They remind astronomers to question assumptions, analyze biases, and explore multiple scenarios. Yet, the weight of evidence favors a distant massive planet. Its influence explains multiple phenomena, predicts future discoveries, and unifies observations that otherwise appear unrelated. While the outer solar system remains largely unseen, the unseen is beginning to reveal its structure, with Planet 9 standing as the most compelling architect of motion beyond Neptune. Even in the absence of direct detection, the cumulative effects on distant objects point toward a coherent explanation. Extreme orbits, resonances, tilts, and clustering all converge in a way that suggests a single massive force. Alternatives, while valuable to explore, consistently fall short in reproducing the totality of observed phenomena. Planet 9 remains the hypothesis that best accounts for the evidence, guiding both observation and expectation. The outer solar system, once thought to be a simple collection of icy bodies, emerges as a complex, interconnected environment shaped by hidden influence. Planet 9, whether eventually seen or inferred through subtle gravitational clues, exemplifies how unseen forces govern cosmic architecture. The alternatives illustrate challenges in interpretation, but the planet's predicted presence provides clarity, prediction, and a unifying explanation that remains unmatched. Today, the search for Planet 9 is more systematic than ever. Large-scale surveys scan the sky with unprecedented coverage and sensitivity. Projects like Pan-STARRS, the Dark Energy Survey, DES, and the upcoming Vera C. Rubin Observatory, known for the Legacy Survey of Space and Time, LSST, are designed to capture faint light from distant objects. Each survey images vast areas repeatedly, building a dynamic map of the outer solar system over months and years. Pan-STARRS, based in Hawaii, uses wide-field telescopes to detect moving objects. By comparing multiple images over days and weeks, astronomers can identify distant bodies with subtle motion. Even a faint object millions of kilometers away becomes visible when its position shifts against the background of stars. Algorithms automatically flag potential candidates, while human observers verify the movement, eliminating false positives from cosmic rays or instrumental noise. The Dark Energy Survey, conducted from Chile, has a similar approach, but focuses on deep imaging in optical wavelengths. DES observes large swaths of the southern sky, capturing faint light from both distant galaxies and nearby solar system objects. The data, when combined with other surveys, provides a comprehensive view of extreme trans-Neptunian objects. By cross-referencing these observations, astronomers can track candidates over time and gradually refine their predicted orbits. The LSST, scheduled to operate for a decade, will dramatically expand observational power. Its wide field and rapid imaging will cover the entire visible sky every few nights, detecting objects far fainter than previously possible. The repeated imaging allows the detection of slow-moving bodies, providing enough temporal data to confirm orbits with high precision. LSST will transform the search for Planet 9 from sporadic glimpses to continuous monitoring. Observation campaigns are meticulously planned. Telescopes follow predicted paths derived from simulations of extreme trans-Neptunian objects. Each night's schedule prioritizes regions where a planet might exert gravitational influence. Observers consider factors such as atmospheric conditions, moonlight, and telescope availability. Patience is essential. The planet moves slowly, and nights of imaging may yield no obvious detection. Every observation contributes to a larger dataset, each frame a small step toward finding a faint, hidden world. Once candidate objects are identified, verification becomes the next challenge. Astronomers re-image candidates across weeks and months, confirming consistent motion. Follow-up observations use different telescopes to reduce errors. Brightness measurements are compared to predictions based on distance and size, and orbital paths are modeled to see if they match expectations for a massive distant planet. This process eliminates transient phenomena, such as asteroids closer to Earth or variable stars, ensuring that only real, distant objects remain under consideration. Data management is a significant component of modern campaigns. Each survey produces terabytes of images, each containing millions of stars and galaxies. Automated pipelines process this data, identifying moving points of light and calculating preliminary orbits. Potential candidates are flagged for human review, ensuring accuracy and reducing false detections. Collaborative networks allow astronomers worldwide to access data, compare findings, and coordinate follow-up observations efficiently. The scale of observation requires global coordination. A single telescope cannot cover the entire sky continuously, so multiple observatories contribute to overlapping regions. Northern and southern hemisphere coverage is essential, as Planet 9 could reside in any part of the celestial sphere. By combining datasets, astronomers can follow candidates over longer arcs, increasing confidence in orbital calculations and improving the chances of detection. Patience underpins every campaign. Planet 9 moves slowly. Its apparent shift may be just a fraction of a pixel over several nights. Detecting it requires careful comparison of images separated by weeks or months. Even after identifying a candidate, confirmation can take years, as observations must rule out background stars, galaxies, or artifacts. Long-term planning ensures that telescopes revisit the same regions consistently, building a temporal record that gradually reveals the presence of distant objects. Astronomers also account for observational bias. Not all regions are equally observable. Some areas of the sky are blocked by the Milky Way's dense star fields, while others are inaccessible due to geographic location. Surveys adjust for these limitations, simulating coverage to understand which regions have been well observed and which remain undersampled. This awareness guides future observations and ensures that gaps in coverage do not conceal potential discoveries. The search is methodical, but also adaptive. New extreme trans-Neptunian objects discovered in one survey can redirect attention to specific regions of the sky. Each finding informs models of the planet's possible orbit, refining the search area. Surveys become iterative. Predictions lead to observations, observations refine models, and models guide further observations. This cycle continues, slowly narrowing the vast search space, a careful dance between theory and measurement. Modern campaigns integrate multiple wavelengths. Optical surveys detect reflected sunlight, while infrared observations capture residual heat from distant objects. Some telescopes operate in both regimes, maximizing the probability of detection. Infrared imaging is particularly valuable for cold, distant objects that emit little visible light. Combining these approaches allows astronomers to detect candidates under conditions that would hide them from a single observational method. Collaboration extends beyond telescopes. Data analysis involves teams of astronomers, computer scientists, and statisticians. Automated software identifies motion, filters noise, and calculates preliminary orbits, while human experts validate findings. Cross-validation ensures reliability and reduces the chance of spurious detections. Large-scale searches require both technology and human insight, each complementing the other to reveal faint celestial objects. Even with powerful surveys, failures are common. Nights of imaging may reveal no new candidates. Many flagged objects turn out to be distant stars, galaxies, or observational artifacts. The search is incremental. Each step builds on previous work, gradually improving coverage, refining detection methods, and accumulating evidence. The process can be slow, sometimes frustrating, yet every negative result contributes to a more complete understanding of the outer solar system. The hunt for Planet 9 exemplifies scientific persistence. Observers continue scanning vast regions, refining techniques, and improving models. Even as months and years pass without direct detection, each image contributes to knowledge of extreme trans-Neptunian objects and the structure of the outer solar system. Patience, precision, and collaboration define the effort, combining modern technology with the enduring curiosity that has driven astronomical discovery for centuries. Observational campaigns are both technical and artistic. Choosing when and where to observe involves understanding celestial mechanics, atmospheric conditions, and the subtle behavior of faint light sources. Observers must anticipate when a candidate may be visible, account for overlapping star fields, and optimize exposure times. Each night of observation is a careful orchestration, balancing resources, timing, and uncertainty in a quest to reveal the unseen. Success in these campaigns requires consistency. Even after detecting a candidate, continuous monitoring is necessary to establish a reliable orbit. Confirming the presence of a distant planet cannot rely on a single night's observation. Data from multiple surveys, different telescopes, and varying conditions must converge to form a coherent picture. This long-term approach transforms fleeting observations into a credible detection framework. Ultimately, modern observational campaigns demonstrate the combination of scale, precision, and patience required to detect faint, distant planets. Surveys like PanSTARRS, DES, and LSST provide the tools, while careful planning and repeated observation provide the methodology. Every image, every flagged object, and every follow-up observation contributes to the gradual uncovering of the outer solar system, inching closer to revealing a hidden, massive world beyond Neptune. The search for Planet 9 is entering a new era. Upcoming telescopes promise sensitivity far beyond current capabilities. The James Webb Space Telescope, though primarily focused on distant galaxies and exoplanets, can provide valuable infrared observations of the outer solar system. Its ability to detect faint heat signatures from cold, distant objects could reveal candidates invisible to traditional optical surveys. Meanwhile, the Vera C. Rubin Observatory, with the legacy survey of space and time, will revolutionize sky coverage. Its wide field of view and rapid imaging will monitor the entire visible sky repeatedly over 10 years. Objects moving slowly against the background stars, including Planet 9, will gradually reveal themselves. LSST's repeated imaging ensures that even subtle motion can be detected, allowing astronomers to map the outer solar system in detail never before possible. These technological advances will increase both sensitivity and coverage. Fainter objects can be detected, and regions of the sky that were previously undersampled will now be observed consistently. The combination of repeated imaging and advanced detection algorithms will provide temporal and spatial data crucial for confirming distant candidates. Each new telescope adds layers of precision, filling gaps in our understanding of the solar system's outer reaches. Direct imaging of Planet 9 may finally be within reach. Infrared detection is especially promising because the planet, despite its distance from the Sun, radiates residual heat. With sensitive instruments, astronomers can isolate faint thermal emission from background noise. Detecting this signature requires careful calibration and multiple observations, but it offers the potential to observe the planet directly, rather than inferring its existence solely from orbital patterns. Advanced surveys will also improve orbit refinement. As more extreme trans-Neptunian objects are discovered, models of Planet 9's orbit become increasingly precise. Each new observation helps narrow the possible locations, guiding telescopes to the most promising regions of the sky. Predictive models, combined with precise imaging, increase the likelihood of detecting the planet efficiently rather than scanning the sky blindly. Future prospects extend beyond a single telescope or mission. Multi-wavelength observations, combining optical, infrared, and even radio data, provide a more complete picture. Each method reveals different aspects of distant objects, from reflected sunlight to thermal emission. Cross-referencing these datasets reduces uncertainty and strengthens the confidence of any potential detection. The integrated approach maximizes the chance of confirmation. Upcoming missions also benefit from improved computational techniques. Modern simulations can model the interactions of thousands of distant objects under Planet 9's gravity over millions of years. By predicting specific regions where the planet's influence is strongest, astronomers can focus observation efforts more effectively. Advanced algorithms track moving objects automatically, filtering false positives and identifying genuine candidates with greater reliability than ever before. The long-term monitoring of the outer solar system allows for pattern recognition on unprecedented timescales. Repeated imaging over years will reveal subtle motions and alignments, gradually building evidence of the planet's presence. Patience remains essential, but the combination of continuous observation, powerful instruments, and sophisticated data analysis promises progress at a rate far beyond what past surveys could achieve. Collaboration across observatories and continents will accelerate discovery. Multiple telescopes observing the same candidate can confirm motion and orbit quickly. Sharing data in near real time allows astronomers to track distant objects efficiently, reducing the time between detection and confirmation. Global networks enhance both coverage and verification, ensuring that no promising candidate is overlooked. Advances in sensitivity will also permit the discovery of smaller companions or distant objects that may have been missed in previous surveys. These discoveries refine models of the outer solar system's structure, helping astronomers understand not only where Planet 9 might be, but how it influences other bodies. A richer map of distant icy worlds provides context, revealing the gravitational landscape that shapes their motion. Direct imaging would allow astronomers to measure brightness, size, and possibly composition. Thermal observations can indicate temperature, while reflected light provides clues to surface properties. Combining these measurements yields a more complete understanding of a distant planet's characteristics. Observing Planet 9 directly transforms it from a theoretical object into a tangible world, visible and measurable like the planets closer to the Sun. Future prospects also include adaptive observation strategies. As data accumulates, predictive models become more refined. Observers can adjust survey priorities based on new discoveries, focusing on regions where Planet 9 is most likely to appear. This iterative approach combines real-time feedback with long-term planning, increasing efficiency while maintaining comprehensive coverage. The potential for discovery is enhanced by technological synergy. Space-based telescopes, ground-based wide-field surveys, and high-precision computational models complement one another. Each instrument contributes unique information, collectively providing a detailed and dynamic map of the outer solar system. Together, they create the best possible conditions for detecting a faint, distant planet. Advances in detection sensitivity will also allow the discovery of unusual orbital patterns. Smaller extreme trans-Neptunian objects may reveal subtle gravitational effects, providing indirect confirmation of Planet 9's mass and location. Even if the planet itself remains faint, its presence will continue to be inferred from the motion of surrounding bodies. These indirect observations, combined with direct imaging when possible, form a complete approach to discovery. Patience and persistence remain central. Despite unprecedented technology, the planet's slow motion and extreme distance mean detection may take years. Surveys must be repeated, data analyzed thoroughly, and candidates verified with multiple observations. Scientific rigor ensures that any claimed detection is reliable and reproducible. The combination of technology and methodical observation offers the best path forward, yet the process requires sustained effort. Future missions also open the possibility of complementary observations from space probes. While none are currently targeted toward Planet 9, Thermal and optical data from distant missions could intersect with predicted positions. Such incidental detection would supplement Earth-based observations, providing additional confirmation or refining orbital parameters. Multi-platform detection increases confidence in any discovery. The cumulative effect of upcoming technology and methodology is a comprehensive strategy. Surveys will cover more sky, reach fainter limits, and capture repeated images. Simulations will predict the most likely locations, guiding telescope time efficiently. Infrared and optical imaging will complement one another, while global collaboration ensures verification. The result is a coordinated, persistent effort that maximizes the chances of finding a distant, hidden world. Discovery of Planet 9 would mark a milestone in astronomy. It would validate indirect detection methods, confirm models of extreme trans-Neptunian objects, and provide insight into the dynamics of the outer solar system. Direct observation would allow measurements of size, orbit, and temperature, transforming a theoretical object into a real world. Understanding its influence would illuminate patterns in comet trajectories, orbital alignments, and the structure of distant icy bodies. Future prospects are grounded in a combination of advanced technology, refined methodology, and global collaboration. The tools exist, the models provide guidance, and the observational networks are prepared. The challenge remains formidable, but the probability of success has never been higher. Each survey, each telescope, and each observation brings astronomers closer to answering one of the most intriguing questions in modern planetary science. Where, exactly, is Planet 9? The promise of upcoming telescopes and missions transforms the search from speculation to testable science. Enhanced sensitivity, repeated imaging, infrared detection, and sophisticated modeling combine to create an unprecedented observational framework. Patience and persistence remain necessary, yet the tools of the future increase confidence that this distant world, if it exists, may soon be revealed. The outer solar system, long shrouded in mystery, stands ready to yield its secrets to those who watch carefully, night after night, frame by frame. The search for Planet 9 is more than a scientific endeavor. It challenges how we define our solar system. For centuries, textbooks presented a simple model: 8 planets orbiting the Sun in well-defined paths. Beyond Neptune, there was darkness, a sparsely populated region of icy bodies. The possible presence of a massive, unseen planet forces us to reconsider that view. The boundaries of our solar system are not static. They are dynamic, extending into regions we once thought empty. If Planet 9 exists, it would alter our understanding of planetary architecture. The outer solar system would no longer be a distant periphery, but a complex arena shaped by gravitational forces from a massive, unseen world. Extreme trans-Neptunian objects, once considered anomalies, become predictable participants in a gravitational dance. The planet's presence would show that even far from the Sun, celestial bodies interact in subtle and powerful ways. Planet 9 also informs our models of planetary formation. Current theories suggest planets form in disks of gas and dust around young stars, with massive worlds settling into relatively stable orbits. The existence of a distant, eccentric planet implies that the early solar system may have been more chaotic. Interactions with other planets, migration, and gravitational encounters could have flung a massive body outward, leaving it in a remote orbit. This challenges the assumption that planetary formation is orderly, suggesting instead that instability and redistribution are natural outcomes. The potential discovery also has consequences for cometary science. Comets and icy bodies from the Kuiper Belt and Oort cloud are influenced by distant gravity. A massive planet in the outer solar system could periodically redirect comets toward the inner solar system. Understanding these interactions may help explain the frequency and origin of long-period comets, providing context for phenomena that have occasionally impacted Earth. From a cultural perspective, the idea of hidden worlds has always captivated the imagination. Stories of lost planets, distant realms, and undiscovered giants resonate across history. Neptune's prediction, Pluto's discovery, and now Planet 9 fit into a long narrative of human curiosity. The possibility of an unseen world beyond the edge of known space taps into a fundamental desire to uncover the unknown, to see what has been hidden from view, and to expand our sense of place in the cosmos. The hunt for Planet 9 embodies both patience and wonder. Observers scan night after night, tracking faint motions, analyzing subtle patterns, and refining models with each new discovery. The work is meticulous, methodical, and often slow, yet it is infused with the thrill of potential revelation. Every new extreme trans-Neptunian object discovered is a step closer, a clue in the larger puzzle. The process exemplifies the blend of rigor and imagination that drives scientific inquiry. Scientific implications extend to orbital dynamics as well. The gravitational reach of a distant planet affects the structure of the outer solar system over millions of years. Extreme orbits, tilts, and clustering of icy bodies are not random. They are shaped by forces beyond immediate perception. Recognizing this influence challenges the notion that distant space is inert or simple. Even at the edge of our solar system, interactions are ongoing, and hidden worlds leave measurable fingerprints on surrounding objects. The existence of Planet 9 would also prompt re-evaluation of observational methods. Finding such a distant, faint planet demonstrates the power of indirect detection. Astronomers no longer rely solely on direct imaging, but combine motion analysis, orbital patterns, and statistical modeling. This paradigm emphasizes the importance of subtle evidence, where clues accumulate gradually to reveal a coherent picture of unseen phenomena. Beyond science, the search has a philosophical dimension. It reminds us of the limits of perception. For centuries, the outer solar system was invisible beyond practical observation. Technology, patience, and careful analysis gradually push those limits. The planet, if found, becomes a symbol of what lies beyond immediate knowledge. The universe is larger, more intricate, and more surprising than our senses alone suggest. The cultural fascination continues because discovery is ongoing. Unlike ancient planets or known bodies, Planet 9 remains elusive. Its absence from direct view preserves mystery. The hunt itself has meaning, inspiring curiosity, debate, and speculation. Each new candidate object, each refined orbit, and each simulated prediction keeps the question alive. Humanity is drawn to this unknown, compelled to observe, calculate, and imagine. If Planet 9 is confirmed, it would reshape textbooks, models, and our mental map of the solar system. It would demonstrate that even in our cosmic neighborhood, significant surprises remain. Knowledge of a distant, massive planet expands our understanding of planetary formation, gravitational dynamics, and the structure of the outer solar system. It becomes a touchstone for future research, informing everything from comet behavior to the evolution of distant icy bodies. The hunt emphasizes the interplay of observation and inference. Astronomers must combine multiple lines of evidence: orbital clustering, statistical analysis, simulations, and direct observation to arrive at reliable conclusions. Each method contributes a piece of the puzzle, and together they build a coherent, testable model. This approach exemplifies modern scientific methodology: careful, deliberate, and incremental, yet capable of revealing profound truths. Even without direct detection, the influence of Planet 9 can be observed. Extreme objects move as if guided by a hidden force. Their alignments, tilts, and resonances suggest a coherent structure imposed from afar. This indirect evidence is compelling, showing that even at the edge of perception, gravity leaves a trail. Observers follow these subtle clues, translating motion into knowledge and gradually bringing the invisible into focus. The outer solar system is no longer a simple void. It is a complex environment where unseen forces shape the orbits of icy bodies. Planet 9, whether eventually seen or inferred through motion, serves as a reminder that the cosmos is vast, layered, and full of structure beyond immediate detection. Its potential existence challenges assumptions, extends our understanding, and illustrates the dynamic interplay of observation, modeling, and discovery. Discovery would also inspire renewed exploration. Telescopes and missions would refine measurements, track additional bodies, and investigate the planet's composition and thermal properties. Each step would illuminate processes at the far reaches of the solar system, providing insight into conditions where light is faint, gravity is subtle, and time is measured in millions of years. The outer solar system becomes a laboratory for understanding planetary systems in extreme conditions. The hunt remains open-ended. Even with the most advanced surveys, the planet may continue to elude detection. Its slow motion, extreme distance, and faint light make observation difficult. Yet, the pursuit is meaningful. Each discovery of a new extreme trans-Neptunian object, each refined orbit, and each model iteration strengthens the search. Knowledge accumulates incrementally, revealing structure in what once appeared random. Ultimately, the search for Planet 9 illustrates the interplay between science and imagination, patience and discovery, known and unknown. It challenges how we define the solar system, informs models of planetary formation, and captures the cultural fascination with hidden worlds. The hunt continues because the universe remains largely unexplored, and each step toward understanding reshapes our perspective. The outer solar system, once perceived as a distant and inert frontier, now emerges as a realm of dynamic forces and hidden giants. Planet 9, whether eventually observed or inferred, stands as a testament to human curiosity, persistence, and the capacity to uncover truths that lie far beyond immediate perception. It reminds us that the cosmos is larger and more complex than previously imagined, and that even at the edge of our knowledge, the unseen exerts influence. In the end, the search is both scientific and philosophical. It invites us to look beyond familiar boundaries, to follow evidence where it leads, and to embrace the uncertainty that accompanies exploration. The outer solar system holds secrets yet to be fully revealed. Planet 9 is one such secret, a possibility that extends the limits of what we know and challenges us to continue observing, questioning, and imagining. The hunt remains unfinished, but its pursuit shapes our understanding of the solar system. Each observation, each simulation, and each discovery builds toward a more complete picture of the outer reaches. Whether the planet is ultimately seen or only inferred, the process itself illuminates the dynamic, interconnected nature of the solar system, reminding us that the cosmos always has more to reveal than our current perspective allows. The allure of discovery endures. Planet 9 represents the unknown at the edge of the solar system. Its possible existence invites further exploration, reflection, and study. The planet's gravity shapes distant objects, yet it also shapes our curiosity, guiding scientists toward deeper questions about formation, motion, and the architecture of our cosmic neighborhood. Even as technology improves, patience remains central. Detecting a faint, distant planet requires observation over years and decades. Each image contributes a piece of evidence. Each simulation provides guidance. The search is iterative and ongoing, a careful, persistent effort to uncover a world that exists far beyond the familiar planets of the solar system. In this sense, Planet 9 is more than a hypothesis. It is a symbol of exploration, representing both the limits of human knowledge and the capacity to expand them. Whether the planet is ultimately found or remains unseen, the pursuit illustrates the evolving nature of science, the cumulative power of observation, and the enduring fascination with what lies beyond the edge of perception. The hunt continues. The planet may yet reveal itself, or it may remain hidden, inferred only through its subtle influence. Either outcome reshapes our cosmic perspective. The outer solar system, once a distant backdrop, now emerges as a complex and structured environment, governed by forces both visible and invisible. In seeking Planet 9, we confront the unknown, pursue understanding, and continue the timeless human endeavor to illuminate the dark reaches of our solar neighborhood.